Good morning. I see a very less number of students. Alok, can you unmute yourself?
Yes, ma'am.
Yeah, Alok, any idea why students are not there in the class?
No, ma'am.
Is there any quiz today or some exam?
Ma'am, our subgroup has a quiz. Don't know about the whole class. We don't have a quiz for a whole class today.
Okay. Anybody else who has an idea? Dhruval?
Yes,
Yeah,
ma'am.
Kapish.
ज्वाइन करते होंगे मैम, अभी क्लास थी पहले.
Abhi class thi, but
Yes.
it's only 1/4, even less than 1/4. It appears only just 2 groups coming up. Let me start out and we will wait for a couple of minutes. What we are going to do today is going through the MOS technology. So I have brought in today a PPT and we will see some PPTs and we'll try to do something beyond it as required, because this is a bit of review which you should have done in your first year, second semester during electronics engineering, but since you missed it out, so I am trying to do it. Yeah, Kritik Ajmani.
Yes, ma'am.
What went wrong? तुम्हारा जो वीडियो है वो कुछ अच्छा सा कुछ नहीं दिखा रहा भाई.
मैम ऑफ कर दिया, हम गलती से हो गया था.
देखो, कोई बात नहीं, प्रोटोकॉल फॉलो किया करो बच्चे.
Okay.
Okay, so I'm starting with the MOS technology and thereafter we will do BJT. And MOS technology, I am sure you know the transistor, but I am still making a quick review. So these are the PPTs which I have taken from the PPTs of Toki. This is the book you can see in the footnote, Digital Systems, Principles and Applications. Here you can see, this is the title of the book. And let me find the laser. Yeah. So this is the title of the book. And there are 3 authors you can see, Toki, Widmar and Moss. And this is the best book by far, which I believe in this topic, which is digital integrated logic families. Or you can pick up some stuff from Mano. Some stuff like RTL and DTL is only given in Mano, not given in Toki. Everything else is given in Toki, and this is what I am going to follow. So MOS technology derives its name from the basic structure, what it has. You know, there is a metal electrode over a oxide insulator, which is formed over a silicon or a typically a silicon, which is a semiconductor substrate. Okay, so today, even this metal electron does not exist in MOSFET, and metal electron has been replaced by a amorphous silicon layer, and this amorphous silicon is very highly doped in a degenerate level to make it behave like a metal. So transistors which are formed by this MOS structure are called field effect transistors. And this is the abbreviation, you know it. The electric field on the metal electrode side of the diode of the MOS structure has an effect on the resistance of the substrate. What does it mean is basically when you apply a voltage on the metal, which is metal is the gate. So when you apply a potential on the gate, either you form a conduction layer beneath it in the semiconductor region, or you don't have a layer. So if you have a conducting layer, this is known as channel, and the transistor conducts. If you do not have a channel or the conducting layer, the transistor cannot conduct. Conduction is when your current can flow from drain to source or source to drain as per our convention. So if I'm talking about NMOS transistor, the current flows from drain to source. Okay. Though electrons flow from source to drain always. Electrons means carriers. So in NMOS, carriers are our electrons. So they flow from source to drain. In PMOSFET, the carriers are P holes, which flow again from the source to drain. And the current in PMOS is typically from source to drain. So these are the basic things which you have already done. Yes. Okay, most of the MOS integrated circuits are constructed entirely by MOSFETs and no other component is used. Typically, it is the scene, and we are not talking about those devices which take or use any other component. Okay, we are talking about circuits where we use only MOSFET. MOSFETs are relatively simple and inexpensive to fabricate. They are very small and consume very little power. This is the characteristics of the CMOS, that it consumes very less power. Earlier in old days, in 80s, this technology was not so popular as compared to TTL was because of its current driving capability. It used to consume low power, but had also the low current driving capability. So typically the IOs, which are the input and output nodes of the device, especially the output node, which has to drive a output capacitive RC load, they were not very fast on it. So they were least preferred. But today's technology, it has been overcome. And now CMOS offers much more current drive as compared to BJT. It can offer anything, any challenge can be met. The principal disadvantage of MOS device is basically susceptibility to electrostatic charge. What it meant was, because in you have N and P structures, the details of it we are going to do in MOS integrated circuit course, but just understand that you would have observed electrostatic charge, especially in winter. When you take off your sweater, there is an electric current you feel. At times you are combing your hair and you see a charge in your hair and the comb. Or even if in winters, at times you open the door, and if the door handle is a metallic, at times you feel a current which flows through you. So all this is electrostatic charge, and that kind of a charge, if it comes on a MOS circuit, it just burns off the chip. This used to be a very severe problem until 10 years back or so. But now people have devised methods to protect an IC against these charges. So now it can be minimized. So I don't take it as a very big disadvantage as of today. Then I did talk to you that there are two types of MOSFETs. One is depletion mode, another is enhancement mode. Okay, and in CMOS technology, we use only enhancement mode devices, these ones. Okay, so what are shown over here are two enhancement mode devices. One is N channel, another is P channel. Okay, and here we have shown the fourth terminal, and the fourth terminal is shown shorted with the source here. And here fourth terminal is again shorted with the source, whereas because this is the higher potential node. So in PMOS devices, your substrate is connected to the higher potential node. Here it is connected to a lower potential node. But when we show a three terminal device, we assume that this is not connected to source, but we assume this to be connected to the lowest potential available in the system, which is ground or VSS. Here we assume the substrate to be connected to highest potential node, which is VDD. Okay. Now the direction of arrow indicate either P or N channel. The symbols show a broken line between the source and a drain to indicate there is normally no conducting channel between these electrodes. So this broken line says normally there is no conductivity, but this is only one symbol. You have plenty of other symbols which you can use, and you will recall I had drawn a very simpler circuit which is typically used in digital circuits. This symbols are used in typically analog circuits, but you should know what does it mean. So I am showing you. So N channel is the most fundamental device or element in MOS technology, and drain is always biased positive as compared to source. We have already known this. Now, gate to source voltage is the input voltage. I had talked to you this in the previous class as well, which is used to control the conductivity between drain and source. So it kind of determines where your device is on or off. So you can see over here, if you connect your gate to 0 volt, this channel, there is no conductivity channel, and it becomes a high resistive region between source and drain, and therefore it behaves like an open switch, which is off. And if I connect on gate a logic 1, which means the higher potential VDD, which means the resistance turns down, it is there is a channel, but a channel also has some resistance. So resistance will not be 0, but here you can see resistor is 10 to the power 10 ohm. This is 10 to the power 3 ohm. So it is typically a kilo ohm. So on resistance is quite low, and therefore it behaves like a short, or which means a switch is on and conducting. Okay, so this is the switching behavior, and for P transistor it is just the complementary. Okay, so this operates in the same manner, but all the voltages have opposite polarity. Current has the opposite polarity. Everything has a different polarity. So you need to bias it with a more negative voltage. It has been shown over here. So your gate, when logic low 0, so your VGS becomes negative minus VDD, and therefore if it is minus VDD, it behaves like as if it is. So if it is, this is 0 volt, so it behaves like low resistance path. There is a channel. It behaves like an on switch and conducting. But if you connect it to 1, this VGS becomes 0. So it is like because VT is negative, 0 is not more negative than VT. So it is off. There is no channel. The resistance is very high, and the switch behaves like an open switch. So we are only interested in the switching behavior at this point in time, whether the switch is on or off. Okay, so you can remember that NMOS, for NMOS, you remember it. If it is high, on. If it is 0, it is off. PMOS is complementary. So PMOS and NMOS circuits, they came in 80s dominantly. I have already said we will not go into the details of it. And earlier there were I had mentioned to you PMOS and NMOS technologies emerging, and eventually CMOS became the most popular one. So now coming to the structure design, now in CMOS technology, the basic structure or the most fundamental gate is a NOT gate. NOT gate in CMOS technology is also known as inverter. See here, inverter. So what is the inverter behavior and what is the inverter structure? Now, before I go to the inverter structure, please note that in CMOS, you always will have a VDD, you have a ground, okay? And between these two, one is a P network and another is a N network. And between the two network, you pull out the output. Now, this is always P, which is between VDD and output, and between output and ground, it is N. You will recall, I did tell in the previous class that N transistor can pass logic 0 perfectly, but when you try to pass a logic 1 here, it behaves a bit non-ideal, and the voltage, this, if it is transferring the value, it has to transfer this 0 to this node. So this 0 will not get transferred over here. This will be 1 VT higher. Okay, not 1 VT higher. If you try to pass on the 1, then it will be 1 VT lower. Similarly, if you try to pass 0 through P, it doesn't allow to you to give a perfect 0. It gives you a 1 VT higher voltage, but it is a good pass for high value. N is a good pass for low value. So you always make N network as a lower network between output and ground, and P network between VDD and out. Input, whatever inputs you have in the gate, they all go to P network, they all go to N network. Okay, so this is the basic structure of any CMOS gate. Now, the simplest gate could be a inverter, which has basically, let me use, this is the basic inverter. So you have a input and a 1-bit output. Okay, so this input here is written as what is the voltage on input. So a logic 1 corresponds to VDD and logic 0 corresponds to 0 volt. Okay, now Q1 is the P transistor and Q2 is the N transistor, or they correspond to network. So here you will have just one input. So you will have only one transistor. You can directly translate. If your function has, now this is written as basically O is equal to I bar. So whatever is the number of variables in your expression, that many inputs will go to each network. So here, since there is one input I, so you have two transistors Q1 and Q2 corresponding to it. Q1 is a P transistor, Q2 is a N transistor. So if I apply logic 1, that means this is 1 and this is 1. So this one conducts, make this conducting. So N is on. Okay, so you see N is on. This will be off. So this is off with a high resistance. This has low resistance. And your output will be now what? This is open. So this is an open switch. So this cannot come over here. This is a closed switch. So V out is sunk, or can be synced to 0. So you get a 0 volt. And when you apply logic 0, this is conducting, this is off, non-conducting, high impedance. So you see it on, this is off, so this is on. So VDD can come to output. So on output, you have a VDD which corresponds to logic 1. So when you apply 0, you get 1. When you apply 1, you get a 0. So it is behaving like an inverter. So V out is V in bar. So this is the basic structure. Now, let's come to two input gate. The basic two input gates, there are two gates which are available in CMOS. As such, everywhere you have, every technology has two input gates. But in CMOS technology, a inverting gate is a basic structure. So the inverting gate means you can have NAND, NOR. You cannot have and or directly realized. The technology that does not permit. And if you want a and or gate, you have to have a NAND gate followed by a NOT gate. Similarly, NOR gate followed by a NOT gate will make a OR gate. So NAND gate and NOR gate are fundamental. So how do you draw the NAND gate? So see, the NAND function is this. X is equal to a dot b bar. So you have two variables a and b. That means you need two gates in N network and two gates in P network. And how you will make them? If it is a dot product, that means A and B are in series for N network. Okay, so first you will draw the N network and dual of it is P network. Okay, so since A and B are a dot product, so A and B, the transistors corresponding to input A and input B are in series. So you connect the two transistors in series and the network is realized. And for P, you have to make a dual network. Dual network would mean the transistors who are in series will become in parallel. Those in parallel will become in series. So here the two transistors were in series. Now they will become in parallel. And you can work out this low-high combination. You can see if A and B both are low. Okay, so that means this is open, this is open. So this output will be 1 because both of this are conducting. Okay, so it is 1. If any one is low, so what will happen? This is a series network. Any input is low, there is an open switch. So this cannot work. And if any of this is 0, so that is enough to conduct. So if any one of them is low, even then you get an output high. This is what is shown over here in these two conditions. And when both the inputs are high, then yes, this goes down to 0. And since both A and B are high, these are open switches, so it cannot get connected to VDD. You will note that there is only one path to output, either from VDD to output, or there is one conducting path from ground to output. That is the beauty of CMOS. You do not have VDD to ground path ever in whatever logic state you are, but you never have a path from VDD to ground, and that saves your current. So the what we had written power expression ICC, here ICC is known as IDD, the current drawn from the supply, because the supply is called VDD. There it was called VCC. Here it is called VDD. And this current is 0. IDD is 0. Static current drawn in this circuit is 0. And therefore static power of CMOS is 0. That is what is the most powerful kind of a characteristics which drive CMOS into the market 30, 40 years back. Okay. And NOR gate is a complementary. You can see that A plus B bar. This is what is the function. Now, first we draw the N network. So A plus B means A is in parallel with B. So input A coming over here. This is a transistor with input B. So the two transistors in parallel, one end connected to output, another end connected to ground. And the dual of this is the series. So P transistors appear in series. So this output goes high only on one condition, when this is conducting and this is also conducting. and P transistor conducts when input is low. So when A is 0 and B is 0, only then I can get a output high. So A is low, B is low, your X is high. For any other condition, any one input going high, if this is high, this is open, no connectivity. If this is high, open, no connectivity. If both are high, both are open. Okay, so any high over here will turn on these transistor. So it will provide a connection and the output falls to 0. So this is the basic operation of CMOS inverters and CMOS basic gates. Okay, so the thing is now you can make cross-coupled these circuits to realize anything. I think this is, I am not directly interested. Uh, Now it says, now CMOS IC also provides all the TTL logic functions or any special functions which even TTL logic cannot provide. I'll take you to one example and I'll show you. Now nomenclature will come to later. For example, I want a gate like, I want a function which f is equal to a. Now this is the kind of gate. You will never find this kind of gate available in any of the bipolar technologies. Either you can have AND gates, which means NAND gates, NOR gates, okay? But you can't mix the two functionalities. But CMOS permits you to make a gate of this kind as a single entity. Now, what you need to do is, as I said before, you need to first devise the network for N and then complementary network you use for P. So what you will do is, now here A, B, C. So you need 3 transistors with input A, B, C. Now B and C are in series. So, and this B and C are in series. This branch is in parallel with A, OR with A. So this is my A input. This becomes my B and this becomes my C input. And this is the ground. Here I connect and this becomes my output node, which is F. Now I need, this is my VDD, and from VDD to F, I need to make a P network, which is dual of this. Now to find a dual, now if it is just 1, 2, 3 transistor, I can directly make the dual. But there should be a method. How do you draw a dual network if it is a complex network? So how you do is, you can use the graph theory. So you draw the network for N. So every transistor becomes a branch and every node, this is one node, second node, and third node. Okay, so every source and drain wherever you have, they are the nodes and you can draw the graph. So this is A. And then on this side, you have 2 branches like this. This is B and this is for transistor C. So this is the graph which corresponds to N network. Okay, now I take the P network and I draw the dual network for P. How do I draw the dual network? I need to draw a branch across each of them. Okay. So every branch has to cross a branch. Okay, but I will have one dot in each space. So this is one closed space, one dot. This is left hand side, one space, and this is on right hand side. I have drawn 2, but they cannot be 2. So I will now erase it and I'll redo it. So I have to have 1. This I'll make 1 and this will be 1. So this becomes my network. So this is the dual network that B and C are coming in parallel, and in this parallel network has a series network A. Now another question comes is whether this end should be connected to VDD or this end should be connected to VDD. Okay, one end has to be connected to VDD, another end has to be connected to the output. So the node which has maximum branches getting connected should be connected to VDD. Okay, so I change the color. So here I'll connect, sorry. This one is B, another is C, and in series there is another transistor which is A. Okay, so this A, if I had a large space, I'll connect them over here, and this B can be connected here. This C should be connected here, and this B also should be taken over here. You need to make those connections. One can make it. Okay, that is not a big deal. You can make those interconnections. Okay, so this is the method. Now this is a single stage network. Okay, one inverting structure which realizes a complex function. So any complex inverting Boolean expression, if you have it, it might have any kind of any number of product terms. Okay, so a SOP invert function can be easily implemented. Not just SOP inverter function, even if it is in POS, sorry, invert form, that also can be directly implemented. Like if F is equal to, let's say, A plus B, C plus D bar. So any inverting function you have, that means it has two branches. These two branches are in series. Now this is a parallel. So you have A plus B in series with A plus B. A plus B, C plus D means they are in parallel. A plus B means AB in parallel. So you have a network which is, sorry. Now here it does not make any difference because both the branches have two transistors. So whether I put AB above or CD below doesn't make any difference. But if I had more number of transistors in one, for example, if I had A dot B plus C. So B plus C are the two transistors, so they will be closer to the ground, and single transistor will be closer to the output. Okay, so this is how you draw the network, and you can use any complex inverting function to do it. Any question with anybody? Else we'll move ahead. Now there are like CMOS ICs available for all TTL families, and at times they are even pin compatible. you have functionally equivalent ICs also available, and electrically compatible ICs are also available. So it just depends upon what you want. You want to replace a TTL with a CMOS IC. So what compatibility you are looking for? If you want to take out one IC and you want to put in just at the same location on the board, you want to replace by a CMOS IC, that is also possible. If you want to build a new board with the same functionality, you can do it. And if you want electrically matching compatible parameters, that is also possible. You need to check for the data sheets what we are looking for. The oldest CMOS series is 4000 series, and this used to be by RCA. And another popular series is 14,000 series from Motorola. For TTL series, 74 series is the most popular commercial series, and 54 series is for military operations. So it is more costly. So you will see this kind of 74 HC and HCT are CMOS series which are compatible to 74 series. Okay, so we will again come back to these variety of families and talking about their currents, voltages, etc. to check their compatibilities. If we want to use different ICs from different technologies, then how do we see whether they are compatible or not? This is another CMOS series, ACL. This is a advanced CMOS series, which is again compatible and to TTL series. I think I'll not go into more series by CMOS. We will not talk about. Okay, this I don't want to talk at this point in time. We will come to interfacing a bit later. Let me first go back and review the CMOS, the TTL series first. Okay, now when we come to TTL, I want you, I have only 5 minutes right now. Okay, so I am using a whiteboard to do it. The TTL series. Now, the basic one is RTL. Okay, I had talked to you that RTL is resistor, transistor, logic. Now you will go back and review how do you draw what is the basic gate? First thing is basic gate in RTL. What is the basic gate in RTL? Okay, whether it is NOR gate or it is a NAND gate. Okay, you will find it out. Second thing what you will see is for two input gate. Now I am not mentioning a NOR gate or a NAND gate. You will find out how do I draw the circuit for a two input gate. Okay, you will see there is a transistor which is being used. I will not tell you which transistor. There is a resistive network, and then you connect it to VCC and ground, and to this again you will have inputs connected. So just check out on the basic network, basic gate and the structure. You will find there these resistance values are fixed. Okay, fixed values you have to pick up. And the second thing which you will revise is DTL, diode transistor logic. The same thing again, what is the basic gate and how do you draw a two input basic gate, the structure of it. And I'm telling you the reference is Morris Mano. This you will not find in Toki. Okay, so you should look into Morris Mano, and this book talks about it, and go through it, and we will come back, and we, though I do know it is covered in TTL, you have three configurations. One is totem pole, then you have open collector, and the third one, what is the third one? Anyone who remembers? Tri-state. Okay, so you have three kind of TTL configurations which are available. So every gate in TTL can have three configurations. So every configuration has its own usage and application, that where do you use what. So we will talk about a bit over here. This is where I will start out. This you please do it, because Friday we don't have a class, Monday we don't have a class, and I'm left with only 2 lectures, which is not sufficient by any means. I'll take 1 lecture to go through this, and I need 3 lectures for doing the interfacing, and then I need 1 lecture for hazards as well. So I will engage extra class after 20th as well. I'll require that. And if you have some extra time in the coming week, you kindly let me know, which you hardly tell me. Even if you have a free slot, you never tell me. So 1 class is already pending from long back. In fact, 2 classes are pending, I believe. So I would need some extra time to cover that. So I'll start from TTL logic, and I will expect you to go through this, and anyone who draws it, kindly send me, click a photo and send me on the mail. You know, as usual, the title has to be UEC 612, and send the mail to alpana@thapar.edu. Okay, so I stop over here, and we will continue in the next class. The TTL logic family, a brief review of TTL logic family. My main emphasis is interfacing. How do you interface various logic families? That is what I want to do. There is a question, when will MST quiz take place? Sure, we have not started because I am still awaiting the directions from DOA. Have your other quiz got kind of scheduled? You have to tell me. Somebody, the any CR who is available should unmute and let's talk. Jayanti, can you unmute yourself and we can talk?
Yes, ma'am.
हाँ, बताओ. Can you tell me कि और subjects के quiz schedule हुए क्या?
सिर्फ एनालॉग का हुआ है अभी.
तो एनालॉग का बच्चे जो शेड्यूल हुआ है वो कब हुआ है? अभी कोई हो गया या अभी शेड्यूल ही हुआ है?
एक हो गया है अभी थोड़े दिन पहले, एंड एक 19th को है.
तो वो LMS के थ्रू ही हुआ था?
यस मैम.
तो the class is 200 plus for analog. So 200 को उन्होंने
3 लिंक्स बना लिए थे.
हाँ?
उन्होंने 3 लिंक्स जनरेट किए थे.
हाँ, वो 4 सर्वर हैं अभी. तो वो 4 में से एक तो बहुत जल्दी क्रैश हो जाता है, तो 3 में भी 200 सवा 200 तक का तो हो जाता है. बट यू आर 400 इन दिस कोर्स, तो 400 के लिए वी आर अवेटिंग दैट सर्वर टू बी अप. सर्वर अप हो गया है, नया जो सर्वर आया है उसकी टेस्टिंग चल रही थी पिछले 2 दिन. तो उन्होंने अभी हमको मेल नहीं किया है कि व्हेन कैन वी शेड्यूल आवर क्विज. एज सून एज आई गेट ए ग्रीन सिग्नल वी विल डू इट, एंड आई विल ट्राई टू स्पेस देम. तो अगला एनालॉग का ही खाली शेड्यूल हुआ है, कब है वो?
मैम वो 19th को है एंड सिर्फ एनालॉग का ही हुआ है।
19th को है तो what class will prefer if I kind of do one post Diwali, that means 19 or something, and then we do it every week one, will that be
यस
okay?
मैम,
And we
यस
will
मैम।
segregate the syllabus as well. We will kind of not have all the syllabus in all the quizzes for sure. We will divide the syllabus.
यस
Okay.
मैम।
So that you have to prepare only a portion and you give a quiz. ठीक है?
हाँ जी मैम।
ठीक है। अगर और कुछ इशू है तो बच्चे मेरे को व्हाट्सएप कर सकते हो, मेल कर सकते हो। अगर क्लास पे कोई डिस्कशन होता है और आपका कोई कंक्लूजन बनता है तो वो भी मुझे बता सकते हो। आई एम ओपन टू इट।
ओके मैम, थैंक यू।
Okay, okay. Have a nice day and wish you happy Diwali vacations, all of you. Enjoy your Deepavali and be back after Deepavali. I want to see the more class. Today, I don't like it. It is such a small group which has come up today. But I appreciate at least you 70 people who joined. Thank you.